So I want you to picture your computer screen right now. Like you've probably got this really sleek, modern operating system running, right?
Yeah, high-resolution icons, smooth window animations, probably a dozen browser tabs open.
Exactly. Everything just feels very, now. But imagine opening a single window on that screen and suddenly you're plunging decades into the past.
Oh, it's a wild
It
contrast.
really is.
Yeah.
You're basically watching this old school, entirely text-based mainframe operating system boot up, just line by green line, like absolutely no time has passed. So welcome to today's deep dive.
It's just such a fascinating visual, honestly. Like you're looking at a digital time capsule,
Right.
and it's been perfectly preserved, but it's actively running right in the middle of a standard, everyday, contemporary desktop.
Which brings it to our mission today. We are going to explore this incredible stack of digital evidence we've got. Basically, we have a detailed look at a modern 2026 Windows machine, and it's running an emulator for this legacy system called YIMI Muse ICSP.
Yeah, and we're going to trace the entire journey of this system. We get to watch it wake up, navigate its really rigid text-based interface.
Which is a trip in itself.
Oh, totally.
Yeah.
And then, remarkably, we're going to watch it interact with the modern internet.
But looking at these initial documents, I have to admit, I'm immediately a bit lost here.
Okay, what's standing out to you?
Well, on one side of the screen, I see this very standard modern Windows command prompt running a file called sim390.exe.
Right, the emulator.
Right. But then right next to it, there's this chaotic terminal window, and it's frantically trying to negotiate what does it say, a 3270 terminal type connection.
Yeah, the 3270 protocol.
It's just spitting out green text on a black background. Like, what exactly are we looking at here?
It is entirely jarring to see them side by side like that. So to give us some foundation, we're basically looking at something called the sim390 MUSI demo operator console.
Okay.
Think of it as this completely isolated pocket universe, that sim390.exe file. That's the emulator itself.
So that's the software container creating the universe on the Windows machine.
Exactly. And that chaotic green text is the operator console. It's essentially the control room of the mainframe. If you look at the logs, you can actually see the original copyright dates proudly displayed.
Oh, I see that. 1989 to 2000, McGill University, Montreal, Canada.
Yeah.
But, and this is the wild part, right below those vintage copyright dates, the system's initialization date reads May 25, 2026.
Yeah, it's amazing.
It's like this ghost from the late 90s waking up and just casually checking today's calendar.
That's a really great way to put it. The operating system, it doesn't know it's in the future, it just knows it's being turned on.
But before we can actually use this system, we have to watch it wake up. And looking at the evidence, the boot sequence is incredibly gritty.
Oh, it's deep in the weeds.
Yeah, the logs are just spitting out these deeply low-level hardware commands. Like it says it's enabling the interval timer. It sets the storage size to 1638 4K.
Which is tiny by today's standards.
Right. And then it starts a RAM disk load. It even logs the mounting of virtual disk drives. And then, and this seems important, it initiates the iNet Internet daemon.
Ah, yes.
And it starts creating sockets, port 621 for FTP and port 801 for HTTP. Okay, let's unpack this.
Sure.
Because it feels like we're watching someone hotwire a classic 1990s car engine.
Right inside the trunk of a 2026 electric vehicle.
Yes. Exactly. Like, why go through the trouble of emulating all these specific hardware checks and interval timers today? Why not just double-click and run the program?
Well, what's fascinating here is that to make legacy software work, you can't just run the code on a modern processor. You know, modern computer chips speak an entirely different physical language.
They have completely different architecture.
Exactly. Completely different from the mainframes of the 90s. So you have to trick the old software. You basically build this highly elaborate software bridge that convinces the old operating system that the physical hardware it was originally built for still exists.
Wow. So, like, when the log says it's enabling an interval timer, what is it actually doing?
Okay, so in a real physical mainframe from the 90s, an interval timer was an actual physical hardware chip.
Like a tangible piece of silicon.
Right, a crystal oscillating at a specific frequency on the motherboard just to keep time. And the 1990s operating system is programmed to actively look for the electrical signals from that specific physical chip.
Oh, wow. And obviously that chip does not exist inside a modern 2026 laptop.
No, of course not. So the emulator has to flawlessly lie to the MUS key system. It intercepts the old software's request to check the timer, calculates what the old chip would have said, and hands back an answer in the exact format the old operating system expects.
It's essentially a very complex, very fast translator, just constantly translating ancient hardware requests into modern computer logic in real time.
And it is a remarkably high-stakes translation, too. I mean, if that software bridge stutters for even a microsecond,
What happened?
or, if the emulator hands back data in the wrong format, the entire 1990s operating system realizes the physical hardware is missing. The whole thing completely crashes. Yeah, it is a masterpiece of digital preservation just to keep the lie going.
I see. Okay. And also notice the boot sequence mentions initiating an INET internet daemon and creating sockets. For those of us who aren't network engineers, what exactly is a daemon and a socket?
Good question. So think of a daemon as a silent background worker. It doesn't have a user interface at all. It just sits in the background waiting for a specific task.
Okay, so it's just hanging out behind the scenes.
Right. And a socket, or a port, is basically a specific numbered door on your computer. So when the log says the INA daemon creates a socket on port 801 for HTTP.
Right, the web traffic protocol.
Exactly. It means a background worker has just unlocked door number 801 and is sitting there waiting for web traffic to knock.
Okay, so we have the engine running, the hardware lies are holding up, and the background workers are waiting at their doors, which means it is finally time to get behind the wheel. We're moving from that back-end operator-level console to the user-facing terminal.
The front door of the system, basically.
Right, and this is where the visual aesthetics really shift. Completely. The user connects using a piece of software called Jolly Giant QWS3270, connecting to a local loopback address on port 623. I'm assuming a loopback address just means the computer is talking to itself?
That's exactly. A loopback address is essentially the computer's way of calling its own phone number.
Ah, nice.
Yeah. Instead of sending data out onto your Wi-Fi or out to the global internet, it loops the signal right back into the same machine. It's what allows the modern Windows side to talk to the emulated mainframe side securely.
Got it. And the sign-on screen that greets them is just, it's beautiful. It's this giant ASCII art spelling out the word music, using capitalized M's, U's, S's, I's, and C's.
Classic.
Which the screen note stands for Multi-User System for Interactive Computing / System Product. It's got that pure classic mainframe charm.
It definitely sets a very specific mood.
Yeah, and so the user signs on with the music user id $000, which clearly looks like an admin account.
Oh, yeah. Root access.
But then there is this intense hexadecimal challenge code on the screen. DF76B4 F262448E3D. What is the point of that massive string of characters?
Okay, so that hexadecimal code, which is really just a numbering system using 0 through 9 and letters A through F, that's an old-school security handshake.
Like before modern passwords.
Well, before the widespread use of modern encrypted passwords over networks, systems would generate a unique randomized challenge code like that. And the user would often have a physical code book or maybe a separate little hardware token to calculate the correct response.
Oh, like a two-factor authentication token from the 90s.
Exactly. It ensures that the person logging in is actually authorized, not just someone who guessed a password.
That makes sense. So once they pass that challenge, we finally see the support tasks. ADMI main menu. It even has a little text-based calendar showing May 2026.
Right, noting it's day of year 145.
And below that, it's just a numbered list. Option 1 for information and statistical functions. Option 2 for working with userids. Option 3 for working with the file system. All the way down to Option 12, the music operator console.
It is a very strict, highly hierarchical menu design.
Yeah, and honestly, I have to push back on this interface for a second.
Oh, how so?
Well, as someone completely used to swiping, tapping high-res icons and, dragging windows around, this green screen, purely text-based menu system looks incredibly rigid. Like, does navigating by explicitly typing 1 for information or 2 for userids actually offer any real advantage? Or is it just nostalgic friction? It feels like it would take forever to get any actual work done.
I get that. It is really easy to view it that way from a modern perspective where absolutely everything is visual, but I would argue it's actually the opposite of friction.
Really?
Yeah, this is ruthless efficiency. Think about a graphical user interface today. You have a massive amount of overhead. Your computer is constantly rendering graphics, tracking the exact coordinates of your mouse movements, running smooth animations.
I guess that's true, yeah.
Here, every single keystroke has a specific, immediate purpose. There is absolutely no bloat.
So it's just purely functional.
Highly functional. When you type 2 and hit enter, it executes the command directly in the system's memory. For an experienced administrator who has memorized all those numbers, their hands never have to leave the keyboard.
Oh, wow.
Yeah, they can navigate layers deep into the system, configure a user, and back out again in the time it takes a modern user to simply locate and drag their mouse across a high-resolution screen just to click a settings gear.
Wow. Okay, so it's less like a modern touch screen, which requires you to constantly look and react, and more like playing a piano.
Yes.
Like once you know the chords and the keys, you don't even look at your hands, you just play the system.
That is a perfect analogy. It is direct command execution without the heavy camouflage of a graphical interface.
Well, we've established that this is a perfectly preserved, isolated pocket universe running efficiently on its own logic. But the ultimate test of any system isn't how it talks to itself. It's whether it can speak to the outside world.
Right.
And that brings us to the web browser and the sources. The user is at a command line inside this old mainframe, and they simply type web/http.httpforever.com.
And suddenly, this completely enclosed, decades-old mainframe is reaching out to the global internet.
Which is crazy. And incredibly, it actually succeeds.
It really does.
Yes. The sources show the AUEECSPW web browser. It renders the httpforever.com website entirely in text. There are no images, no CSS styling, no pop-ups, just pure raw data.
And the content of the website itself is amazing. It proudly calls itself a reliably insecure connection.
Right, which sounds a bit terrifying until you read the text explaining why it exists.
Yeah, context is key there.
Exactly. The text on the site explains it was built by a security researcher named Scott Helm as a captive portal buster. The site says, if you're on a train, in a hotel or bar, on a flight, or anywhere that you have to log in for Wi-Fi, this site could help you.
And the problem this site solves is a deeply frustrating modern one.
Oh, I hate hotel Wi-Fi.
Right. When you connect to public Wi-Fi, the network often wants to intercept your connection to force you to look at a login page or agree to their terms of service. That mechanism is called a captive portal.
Okay.
But almost all modern websites today exclusively use HTTPS, which is highly encrypted and secure.
And what happens when a captive portal meets HTTPS?
They absolutely clash. If a hotel Wi-Fi router tries to intercept a secure HTTPS connection to show you a login page, your modern browser just panics.
Because it thinks it's an attack.
Exactly. It sees a third party, the hotel, trying to inject data into a secure channel. It views this as a man-in-the-middle cyber attack. So your modern browser throws up a massive red warning screen saying your connection is not private, and it actively blocks you from clicking through to the actual hotel login page. You are just stuck.
Here's where it gets really interesting. It's like we have this incredibly secure, modern smart lock on our digital front door. That's the HTTPS.
Right.
But when we stay at a hotel, that smart lock actually traps us inside the lobby. It refuses to let the hotel's network talk to us to unlock the door.
Yeah.
So Scott Helm built a wooden skeleton key, a deliberately unencrypted HTTP site, just to trigger the hotel's login page without setting off the modern security alarms.
And what is truly beautiful about this moment in our evidence is the irony. You have a very specific 2026 security workaround, a site that intentionally relies on an outdated, insecure, unencrypted protocol and is being perfectly rendered by a decades-old mainframe operating system's text browser.
Because the mainframe doesn't even know what HTTPS is.
Yeah.
It doesn't have the modern security alarms to trigger. It just sees plain old HTTP, says I know that language, and fetches the page flawlessly.
It is a moment where the distant past and the modern present perfectly align to solve a contemporary headache.
It's so cool.
It really is. The mainframe browser strips away all the visual clutter, ignores modern security panic, and just delivers the raw payload of the site.
So after reaching out to the global internet and breaking through modern captive portals, the user in our evidence turns their attention back inward. They dive back into the system's own isolated ecosystem to look at the mail facility.
Yeah, the navigation takes them to an option reading mail for and then an arrow pointing to the new dollars.
The journey walks us through creating a new message. And again, there are no pop-up windows, no rich text formatting, no emojis. It is a clunky line-by-line text editor.
Very old school.
Very. The user, acting as the admin, sets the to field to $1,000, meaning they're basically sending an email to themselves on the exact same system. They type a subject line, hello from 2026. Then they jump into the text editor, which is visually just rows of equal signs marking the blank lines on the green screen, and they type out a single line of text. Hello, admin, this is Jim.
It is the absolute bare minimum architectural requirement for a digital message. You have a sender, a recipient, a subject, and a payload. Nothing else.
Right. And they drop down to the command line, type send, and immediately a notification pops up on the screen surrounded by dashes. Mail has arrived for you from Civil Dollars at Music.
That's fast.
Instant. They open the message, and you can see the raw headers. Date, Monday, 25 May, 2026, and the metadata identifying the software. X-Mailer, USI CSP V6 22.0.
That Xmailer tag is a fantastic detail, by the way.
Oh, yeah.
Yeah, it's a standard email header where the system is proudly stamping its specific identity and version number onto the message before delivery.
So what does this all mean? Like, think about your own phone. You send hundreds of instantly delivered blue bubbles a day, and you probably never think about the infrastructure making it happen.
No one does.
Right. But seeing this bare bones, instantaneous internal delivery within this simulated mainframe, it feels almost like discovering fire. It is the absolute raw mechanics of digital communication, completely stripped of all its modern gloss. How is this message actually moving from Jim to the admin if it isn't going over the internet?
Well, this raises an important question about how much invisible architecture we take for granted today. When you send an email now, it goes from your phone up to a cloud server, gets routed through DNS servers, passed through SMTP relays, and pushed down to another device.
That's a huge journey.
Massive. But here in MUSI CSP, when the user manually types the send command, there is no network involved.
So where does the text actually go?
The system is literally taking that string of text, hello admin, this is Jim, and writing it directly into another user's spool on the exact same local hard drive.
Oh, wow. Just a file transfer.
Exactly. And the moment that file updates, it triggers an interrupt in the system that pops up the notification on the screen. It is the purely digital equivalent of slipping a piece of paper under your roommate's bedroom door.
You are forced to interact with the very bones of the concept. There is no graphical camouflage hiding the file system. It reminds us that underneath every slick modern messaging app, there's still just a computer passing text strings from one database address to another.
We have seen the mainframe consume a modern website, and we've seen it route mail to itself locally. But the final piece of evidence in this deep dive is definitely the most surprising. We actually see the mainframe acting as a provider to the modern world.
It is the ultimate role reversal for a legacy system.
It really is. Think back to the very beginning, in the engine room, when we saw that INA background worker daemon starting up. The operator console specifically noted it unlocked a door, a socket on port 801 for HTTP.
Right, the log read 801 for TCP, HTTPDA. That is the HTTP daemon just waiting to serve web pages.
Well, in the final document, we are out of the green screen terminal entirely. We are looking at a modern, sleek Google Chrome browser window running natively on the 2026 Windows desktop. And look at the URL bar. It says 192.168.1.244.801. Wow. So that IP address and port number mean modern Chrome is bypassing the internet entirely and connecting directly to that background daemon waiting inside the emulator.
Yes. And what Chrome is displaying is this minimalist black and white web page titled Sample Web Page. The only text on the page says, actual file name is $1,000 http home.html. Wait, I want to make sure I really understand the gravity of this.
Go for it.
The emulator isn't just a toy we're looking into. It's not just a closed loop for nostalgia. It is actually broadcasting out. It is actively serving web pages to a modern browser in 2026.
If we connect this to the bigger picture, this completely shatters the illusion of digital time.
How so?
Well, we tend to think of computing history as a straight line, right? Where old things are replaced and they just die. But this proves that digital environments aren't defined by their age. They are defined entirely by their protocols.
Okay, I'm following.
HTTP Hypertext Transfer Protocol is a universal standard. It is literally just a set of rules for how to format and send text over a connection.
It is the foundational lingua franca of the web.
Precisely. Because the Muser CSP mainframe was programmed to speak the rules of HTTP, and it has an active daemon listening on port 801, modern Chrome has absolutely no idea that it is talking to an emulated ghost from McGill University originally coded in the 1990s.
That's so funny.
And frankly, Chrome doesn't care. Chrome just reaches out, asks for the HTML document using standard HTTP rules, the mainframe replies with the properly formatted text, and Chrome renders the page perfectly on a 2026 monitor.
So Chrome genuinely thinks it is talking to a modern web server.
Yep.
And the mainframe genuinely thinks it is serving a page to a contemporary client from its own era. They're separated by decades of computing history and entirely different hardware architectures, but they are completely united by a shared protocol.
It showcases the incredible resilience of these foundational internet standards. You know, the physical hardware changes, the microchips get infinitely faster, the interfaces evolve from rigid green screens to high-definition touchscreens.
But the underlying agreements on how computers pass text back and forth remain astonishingly stable.
Exactly. The bedrock of the internet hasn't moved.
It is a beautifully closed loop. I mean, we started this journey by watching a relic boot up inside a modern emulator. We unpack the complex hardware lies and fake interval timers required just to make the old software think its physical body still existed.
Right, and then we navigated the ruthless efficiency of its ASCII menus, decoded hexadecimal challenge handshapes, and saw the raw speed of a purely keyboard-driven system.
And then we watched it use a text-based web browser to solve a modern Wi-Fi problem, interacting with a modern 2026 website built specifically to bypass today's strict security protocols.
Which was so clever.
So clever. We saw a user named Jim send a raw, unabstracted internal memo to himself by writing directly to a local disk. And finally, we watched the relic step out of its isolated box and confidently serve a web page directly to Google Chrome.
It is proof that a ghost in the machine never really dies, as long as it still remembers how to speak the right language.
It is a lot to process. So as you look at your own sleek, modern screen today, take a hard look at the apps and operating systems you're running right now. The polished interfaces, the complex graphical environments, the secure smart locks. In 30 or 40 years, which of today's digital environments will still be meticulously emulated by curious minds?
That's a great question.
And more importantly, what entirely new, unforeseen modern problems will they unexpectedly be able to solve when someone opens them in a window decades from now? Keep digging, and we'll catch you on the next deep dive.